Our next speaker is Dr. Katanya Kuntz from Waterloo, who has grown up from Calgary, if I'm not mistaken.
Yes.
So, Dr. Kuntz is a research associate at IQC at University of Waterloo. She is the QEYSSat science team coordinator for Canada's first quantum satellite mission, quantum encryption and satellite and science satellite. Katanya received her PhD in electrical engineering, quantum optics from the University of New South Wales, Australia in 2013, and BSc in physics from the University of Calgary in 2008. She works in the field of experimental quantum optics, such as generating quantum states of light using lasers and nonlinear crystals to study quantum entanglement. She's active in promoting STEM education via outreach in schools, the community, and volunteer work. Without further ado, a big round of applause for Dr. Kuntz.
Thank you. Thank you. Thank you very much. And thank you very much to the organizers, especially Moji. This has been a very wonderful conference, and this is my first in-person talk at a conference in over 3 years. So I feel very fortunate to be able to be here. So yes, my name's Katanya, and we're going to talk about photons in space and the QEYSSat mission today. So I just want to acknowledge the main science team people that I work with. So as I was introduced, I'm in Thomas Yanavine's group as a research associate, and he is the science team principal investigator. Maybe I should point this away from me. Is that better? Okay, I thought there was an echo. And then Brian Moffat is the science team program director. Brendan Higgins is the science team technical lead. Paul Godin is the science team technical specialist, and I am the science team coordinator. And at the end of this talk, you will know why we have all these different roles and what we all do. So I'm going to talk a little bit about what experimental quantum optics is, because I'm an experimental quantum physicist that does quantum optics. And a lot of people kind of look at me when I say that at a party and blink twice and then say, okay. And then I follow it up with, I play with lasers and satellites. And then they go, cool. And then we have a fun conversation. So that's what I want to do with you guys now. So we already had some wonderful talks throughout the day yesterday and this morning talking about what QKD is, and so now we get to take all that information and put it into practical use, because I'm going to actually step us through what a BB84 protocol is if you wanted to implement it in real life. So we saw the theory, now we're going to look at the experimental side. And then to expand on that, we will talk about what satellite QKD is. Then I'll go into the QEYSSat mission, specifically how we are building prototypes in the lab to test ideas and protocols before we actually put them on a satellite, because it's very expensive to launch things into space. So it's good to test as much as you can on the ground or in space-like conditions that you can create on the ground before you actually put something into space. And then talking about the satellite mission, we'll talk about the science teams that I'm helping to coordinate. And then finally, if we have time, I want to talk briefly about our quantum optical ground station, or the COGS, QOGS. And so this ground station is being built at IQC. We actually have some members of our team here, including Wilson. And so he's one of the members responsible for building this, what's called a transreceiver, because it's both a transmitter and a receiver. And also we're going to talk about the two different sources, the main two sources that we're going to be testing, which is this, and creating, which is this weak coherent pulse source and also an entangled photon source. So you would have heard a lot of these terms already, and now we're going to put them all into practice. So I'd like to just begin with a really brief overview of where I was and how I became who I am now in my career. Because obviously for people who are just starting out in their undergrads or already partway through or almost finishing, you want to know like what's out there, what could I do next, right? So I did my Bachelor's of Science in Physics at University of Calgary. Then I went across the world to Australia to do my PhD in electrical engineering, and which is actually specializing in quantum optics. but in some universities, they put your quantum optics people in the electrical engineering department. So that's how I ended up with a degree in physics as well as a degree in engineering. And that worked out really well because this laser stuff is really cool and understanding the physics of it's really, really interesting. But then the actual practical implementations of it experimentally, you need a lot of electronics. You need filtering, you need detectors, you need analyzers. There's a lot of electronics that go into it. So it's really nice to have that combination. Then I came back to Canada and I started as a postdoctoral fellow at IQC, the Institute for Quantum Computing at University of Waterloo, and joined Thomas Yannevine's group in 2015. And now I'm a research associate in his group and the science team coordinator, and also just recently announced a new project called Hyperspace, which I'm not going to get enough time to talk about, but I can answer questions later. And so this is a new initiative that just began. It's a 3-year project, and it's a collaboration between Canada and Europe. And so with the QEYSSat mission, right, we're demonstrating quantum key distribution across Canada, as well as around the world, but the ground stations in particular are in Canada that we're using first. Whereas Hyperspace is trying to make a link from Canada to Europe, like a direct link, using a quantum satellite. And so this would be a future quantum satellite mission. How would we make that happen? So that's something new that's just beginning, and I will be the administrative lead, which is basically like what I'm doing now for the science team, but for a different project. Okay, so just to make sure everybody's on the same page, because I know we have people who are from all different backgrounds, like chemistry and biology, or maybe not biology, but engineering, and as well as physics. So when I say quantum physics, what am I talking about, right? It's this, the study of the tiny, and the study of molecules, and how things are formed, and bonds, and orbitals, and things like this, right? And as well as just keeping in mind that when we look at something in the macro world, the big world, it can look a certain way, but then if we actually look at the microscopic version of it, then it can look completely different. For example, this picture in the bottom right here is chalk. So that's what chalk looks like when you zoom in. So yeah. And there's actually chalk in this room. I love that. Usually it's always a whiteboard. So I could point to it. It's good. And then what is light? Because I said I'm an experimental quantum physicist, or quantum optics. So what is light? So I think we all agree it's an electromagnetic wave, right? It has this range of spectra from the radio waves all the way up to the gamma rays. One in particular we're talking about is the visible range here and the infrared because of telecom communications at 1550 nanometers. And then when we think about light, we can think of it in the classical way, like with waves, right? And we can also think of light in a more quantum way, which is quanta, right? Particle. So if a photon is a particle of light, and then a wave is also like interference waves. Like here is the famous picture of the double slit experiment. And if you guys remember, you have these 2 slits, and then even if you send in individual single photons, eventually you're going to build up this interference pattern. So that tells you that even when a particle of light, a photon is a photon-like particle, it still has this like probability wave associated with it, a wave packet. So there's this really interesting duality between matter and energy and particles and waves. And it gets very, we can harness this to our advantage in quantum technologies. And so as John mentioned yesterday, and I think a few other people would have probably today, when we're talking about the labels that we want to use on for how to code zeros and ones, so we can use different degrees of freedom. We heard about time bin, we've heard about frequency, and there's also polarization. And so just as a reminder, polarization is just a direction, right? It's just a reference frame. So it's aligned to the electric field vector of your electromagnetic wave. And so we're going to use that label to generate some secret keys. So first off, why do we even need quantum key distribution? And I think a lot of the talks before me already motivated this question a lot. So as we've already talked about, the security of QKD, it's not based on computational hardness of solving mathematical problems. It's actually based on physical processes that are not vulnerable to more powerful or better computers or even a quantum computer. So public key encryption, which Fred was talking about earlier, it might not be secure against newer, more powerful computers in the future. So there are actually bad agents out there storing information, waiting for it to be hackable in the future. So the beauty of this QKD stuff is if an encryption key is generated today from a QKD protocol, then it'll remain secure against future attacks. So if it's secure today, it'll be secure in the future as well. This is called forward security. And so what we can do is we use this particle nature of light, the photon, and one photon will carry 1 unit of information. And so that's our quantum bit, or Q bit. And one of the linchpins of why this all works, quantum information can be transferred, but it can never be copied. That's the no cloning theorem that was mentioned before. And also measurement disturbs the state. So if an eavesdropper is trying to attack your signal going between Alice and Bob, and I can use this language because Fred has already explained all this, so thank you, Fred, again. So if you have an eavesdropper there, and the eavesdropper is trying to attack and get a photon from your signal, that will be detected. Alice and Bob will know that that happened. Then they will terminate the protocol and start again, because measurement always disturbs the system. And they can't just take a photon, copy it, and send you a copy back, and you don't notice, because you cannot copy. That's why we can't have, to send signals over long distances, we can't use classical amplifiers like we do with the normal internet right now, because that's basically, amplification is copying. So we have to have nonlinear amplification, which is this, quantum repeaters and quantum memories and things like that. And it's not copying the information, it's storing the information for it to be released later. So big picture, one of the projects that I was involved in the beginning of my postdoc with Thomas was if we were to be implementing one of these QKD protocols, say between 2 boats on the ocean that are separated by a few kilometers, maybe even longer, as long as they have a line of sight. Remember that over the ocean you've got, it's a big body of water, right? So it's a massive heat sink. And so you've got turbulence in the air, because turbulence is basically air moving because of the hot and cold sections of the climate. So if you have a laser beam that's going through the atmospheric turbulence, then you're going to have this problem of the beam wandering and drifting and bouncing around, just like when you're looking at stars in the sky. If you look at stars straight overhead at the zenith, they look very sharp, they look very clear, they don't move too much, right? But if you look at stars near the horizon, they're bouncing around, they're changing colors, you think there's a UFO coming to say hi, right? No, that's actually the turbulence. And so the same thing will happen to our laser. And so what we wanted to do was in the lab use a special device called a spatial light modulator that would simulate what atmospheric turbulence would do to the beam, and then perform a QKD experiment or could perform a measurement of the receiver, for example, and see, okay, what happens. So we have the light coming out of the transmitter here, and you can see this false color picture. So basically, I wish the light looked like a rainbow. It doesn't. It just looks green. But if you take a picture of it, like put a camera in the slice and take a picture of the beam, then you'll have a very bright center, and then it diminishes in intensity towards the sides. So it's a Gaussian beam. And then we have after turbulence, you see this very messy, scattered, distorted thing over here, right? And so this black and white image that you see next to that image, this is the phase map that we put on the spatial light modulator. That, remember when Fred was talking about OAM modes, orbital angular momentum modes, and how the wavefront of the light, it looks like a corkscrew instead of like a plane wave. So you can do other things like put a crazy, messy thing like this, and then you create a phase front that looks like that. And it emulates what would happen if a laser beam was to transmit through the atmosphere. And so now what if a hacker, right, was sitting in a little tugboat or something, you know, and trying to hack Bob? So we look into ways that the physical systems are vulnerable, because even though QKD is theoretically 100% secure, the implementation could have flaws. Those flaws could then be hacked and be vulnerabilities that would allow an eavesdropper to learn your secret key before, and you wouldn't even know. Because, for example, I have a picture of it coming up. One of the very first QKD experiments, it literally hummed a different frequency when it was sending a different state. So you could literally listen and eavesdrop and figure out the code. So we don't want that. And so we want to see, okay, if a hacker is also trying to send a laser beam to do something to your receiver, but their beam has to go through the atmospheric turbulence as well, what would happen? Would that prevent them? Because this particular attack required a very precise angle. And because your laser beam is jumping around, she wouldn't be able to maintain that angle. So this paper that was published a few years ago talks about this experiment, and then this is some of the pictures of the actual device. So like the spatial light modulator is this tiny little LCD screen. So it's an LCD screen that you apply like a voltage to that adjusts the phase of the pixels, and then you get a different phase wavefront. Okay. So that was just a little bit of motivation for what QKD is and why and all that kind of stuff. And so in the bigger picture, I'm going to talk about quantum and space, right? So we have this quantum space race going on. And this picture is actually now 4 years old. So there's even more satellites and more missions going on. I need to find a new one, but nobody's made one yet. So we've got lots of different countries that you can see. They either have missions that are currently in orbit or are coming up. And in particular, we've got the QEYSSat missions here from Canada. And so the plane that you see here, I have some slides of that mission coming up. So that was part of Thomas's group's first airborne demonstrations of ground to space or ground to airplane QKD, and so that experiment led to the development of the QEYSSat mission. So there's been a lot of work in the background in Canada leading up to this big mission. So like I said, I would love it if everybody could walk away from today's talk knowing what QKD is, and if you ever wanted to do it, you could make a little demonstration for yourself. So I'll just step quickly through like a protocol, and then we'll get back to the satellite stuff. So this is that picture of one of the first demonstrations of QKD. And so you've got a light source on the far left here. And then basically you've got a quantum channel, which is this like free space meaning traveling through the air, right? Technically it's in a tube, but it's in the air. And so I think it was like a 30-centimeter channel. And then you've got your receiver and your detectors, A and B. And so, as I said, I believe it was this experiment, or maybe one before this, or after this, sorry, that it would blink, it would hum at a different frequency when the different polarization states were being sent. And so, what is the BB84 protocol, right? So we talked a little bit about it before with Fred's talk. So just a reminder, right, we've got Alice as the sender, and we've got Bob as the receiver. And you've got this quantum channel. And the goal is to do this real-time generation of a random sequence of zeros and ones. That's going to be the same length as the message that you want to send. And I want to be very clear, we're not sending the message at this point. We're just trying to generate the key. Okay, we're just trying to generate this random sequence of zeros and ones, and we want to generate it in real time between Alice and Bob, because that's going to be the fastest, most efficient way to do this, right? It's a replacement of a person literally walking with a briefcase from one to the other with the secret code or the secret keys inside that briefcase, right? Instead of sending a person, we want to send a photon. And we want to send a lot of photons to make up the whole key. So we're going to work in binary still, right? So we got your zeros and your ones. And so the way that we encrypt the message once we have the key is that we take our message, we take our key, and we do an XOR. And so this table shows the XOR results which you would then send. And then your receiver would have the key, right? They would receive the XOR result, this KS, and then they XOR those two things together, and you get the message back out. So, and to an eavesdropper, this XOR result here is just garbly-gook, right? Unless you have the key, it makes no sense. And so you can broadcast that over a public channel, and you don't have to worry about it being corrupted. So as I said, QKD is real-time generation of an encryption key, and one photon carries 1 qubit of information. Okay, and so we can do this in lots of different degrees of frequency, or degrees of freedom. We've chosen, in this case, polarization. So now we need a labeling system. We need zeros and ones. So we're going to call vertical 1, and we're going to call horizontal 0. Remember, light's polarized. It's just the direction of the electric field. And that's fine. So then we have the diagonal and the antidiagonal. So because we need, for this protocol to be safe, if someone was to intercept your photon, and if they don't know which bases, these are called bases, this HV and DA, they're called measurement bases. You'll see why. It makes sense when I show you more of the experiment. But if someone was to measure the photon in the wrong bases, you want their results to be completely random, 50-50. They get no information. This is part of the security. So that's why we need both HV and DA. Because if we only had one, then an eavesdropper could measure it and be sure every time. Okay, so now we're going to step through the protocol. So Alice has a random number generator, preferably a quantum random number generator, because that would be also one of the flaws if there was any kind of pattern in the states being sent. So Alice has to choose between HV and DA. And then Bob has to choose which basis to measure in. And so if it's the HV basis, then if it's a 0, if it's H, then you get a 0. The detector is labeled as a 0. If it's a V, you get a 1. And then this random number generator, this rotator, that's also the random choice of Bob. So Alice has to have a random choice of what state to send, and Bob has to have a random choice of what state to measure. And the difference between the two states is just a rotation, because diagonal polarization is just, vertical polarization or horizontal polarization rotated. So what happens if Alice was to send, say, a diagonal photon, like in this first step in the protocol, which is assigned a 0? And what if Bob, right, because Bob doesn't know what Alice is sending. In an ideal situation, Alice and Bob would be nowhere near each other, right? You're trying to distribute keys with people who could be in different countries. So Bob is just going to randomly choose a basis. This time, Bob chooses the HV basis and measures so it's a diagonal photon coming in, but then Bob measures it in the HV basis, which is the wrong basis, okay? So what happens is that the result that Bob gets, which happens to be a 1, okay, so his vertical detector went click. What happens when a diagonal photon comes into one of these detectors? So you've got this polarizing beam splitter, and what it does is it separates, right, the H and the V polarizations. So, for example, in this picture, horizontal is being reflected down, and vertical is being transmitted through. So if a diagonal photon comes in, well, if you take if you break what diagonal polarization is in terms of H and V, it's 50% H and 50% V, right? But it's a single photon. So it can't split and have half of it go one way and half of it go another way. It's a single photon. This is part of the beauty of quantum physics. So it has to choose. Well, how does it choose? It's purely random. So if Bob measures in the wrong bases, his answer is just purely random. It's noise. And so the second part of the protocol, once you've done this transmission, is down here. It's called public discussion. And so it says, Bob tells Alice the basis choice that he made. And then Alice tells Bob which bits to keep. So she's not saying, I sent a 0, I sent a 1, I sent a 0, I sent a 1. She's not saying that at all. She's saying, in this timestamp, because this is all timed, right? We have like time taggers in our experiments. At this timestamp, I sent something in the AD basis, the diagonal basis. And on this timestamp, it was vertical or horizontal vertical, HV. And then Bob is just announcing what basis choice he made. He's not announcing if it's a 0 or 1. So everything's still safe to say this. And then they decide, okay, if Bob measured in the wrong bases, we discard and we move on. So you just keep doing this. Because it's random, you'll build up enough sequences where you keep the 0s and the 1s because your bases lined up. And then that's what's called your shared sifted key. So now what about Eve, right? Because no one's stopping a random eavesdropper from intercepting a photon and taking a measurement. So what happens when Eve does that? Well, Eve has to make a random choice too. And if Eve chooses the wrong bases, that means that their choice will be wrong. Their answer will be random. And then if Bob, right, Alice and Bob, they're always monitoring the single photon rates of their detectors and of their channel. Because if all of a sudden the rates slow down, well, what happened? Why am I suddenly losing my signal? Did someone intercept it? Or is something broken? Like, what's going on? So if Eve was to intercept a photon, she has to then resend. This is called the intercept and resend attack. She then has to resend something so that Bob and Alice don't get suspicious that something's wrong. So that means if she measured in the wrong bases, she's also going to send a random result back to Bob. That's going to cause the error rate of Bob's measurements, the error rate being how often is it the wrong bases versus the right one. It's going to make that go up. And so, as Fred mentioned in his talk earlier, there's that 11% threshold. Above that, we don't have enough error correction. There's not enough photons to make a viable key. And error correction isn't enough to save it either. So that's part of the beauty of why this works. Because if Eve has to make that choice, she's going to get a random result. Bob is going to know because it causes the errors to go up or the measurements go down. So this is how the protocol works. So now, if we want to expand this to what satellite QKD is, so in our QEYSSat mission, which again is the quantum encryption and science satellite, so it's a trusted node satellite. So that means that QEYSSat will be over top of one ground station first, say in Waterloo, and we'll exchange a key with that ground station. So the ground station will be Alice. And the receiver is actually on our satellite in our mission, which is a unique thing that we're bringing to the team. So that's Bob. And so that will be one key. That'll be key A. And then the satellite will fly over to the other location, say it's in Calgary, and then do another link with that ground station. And then that'll be a separate key. That'll be key B. And then, just like what we did before when we were talking about what would happen if we wanted to send an encrypted message. So for this encryption key, just for the keys, you have one key, key A, you have a second key, and then if you XOR the two together, then you get that result. And you can broadcast that result. And then say there's a mutual understanding between the ground stations that you're going to use key B. So that means to get, for ground station A, to get the key, they just have to take the public announced key and then XOR it with their key A, and then they get key B back, just like showing here. So that's how trusted node satellite QKD works for this. And big picture, why do we want to do this? So, oh, it got cut off a little bit. Oh, just there though. Okay, cool. So in this image, you can see all different types of links. So this is what I'm calling a general overview of the quantum internet, the different link scenarios that are possible. And the one in particular that we're doing with QEYSSat is number 3, where we have a ground station going up to a LEO satellite directly. But you can also have quantum ground station links to HAP. So that's a high altitude platform. So there's lots of exciting experiments that can be done with just being, 3 to 5 kilometers above the ground. And so that's a very viable link that we might need in this QKD system, because as was mentioned earlier, again by Fred, the daylight operation of satellites is also really, really hard because the sun is really bright and we're trying to detect these little tiny single photons that are getting washed out by the noise, right? So when we work, if we have these restrictions of only working at nighttime, it's really good if we have different satellite links, because no one's gonna be happy if they can only log on to their internet banking between the hours of 2 and 5 a.m., right? Like, how is that gonna make customers happy? So you need on-demand keys and all 24 hours a day, and so we need to think about how to implement that in the real world. Other links would be also to HAP to satellite, satellite to satellite, so inter-satellite links, because maybe you'd have a network of links, yes?
This work for polar orbits as well, even like it would require more quantum ground stations, I believe, or would it be cost effective? Would we be able to justify the use of this for polar?
For sure.
Satellites at that point?
Yeah, for sure. So the question is, would these systems work for polar orbits as well as GEO and LEO and MEO orbits? And definitely. So one of the projects that I was involved in, and also my professor, it was called QEYSSat 2.0, and it was looking into what the future satellite missions could be for Canada. And if we want to have coast to coast to coast coverage, because remember we have 3 coastlines, we need some different orbits in the north in order to access those remote stations. Yeah. Okay, so I'm just gonna little fast wrap up, or not wrap up, but I'll stop in about 3 minutes. Okay, yeah. So, and then the other one I just want to point out is this link 4, the double link. So that's from the satellite, if the satellite had 2 transmitters or receivers, and so you could see 2 ground stations at very distinct locations, like in different countries, then that would be very beneficial, because if you had an entangled photon source on your satellite, then you could do entanglement distribution, and you could do satellite QKD with an untrusted node. So that means even if your satellite was to be hacked, you would not lose your security. So the satellite becomes Charlie in this situation, and then you get Alice and Bob sharing an entangled photon pair, and so that would be the ultimate in satellite QKD. So we have to build up to that, because putting sources like that in space is hard. So as I said, the QEYSSat mission, this is a technology demonstrator platform, because this is our Canada's first satellite mission, quantum satellite mission. The main advantages is that it's an uplink channel, so the quantum receiver is on the satellite. It's a 4-state polarization analyzer. There's a diagram down here at the bottom showing that HVDA, as I was talking about before, from the BB84. So we're implementing what's called decoy state BB84, which is like a little bit fancier BB84. And the fancier part allows you to tolerate longer distances, more losses in your channel, and still get a viable key. And if you want to know more about that, we can talk about it later. And so the pass band, the acceptance band of our satellite, is this 780 to 795 nanometers. And then we just recently had a new project announced called RefQ, which stands for Reference Frame Independent Quantum Key Distribution. I think that's all the It's a very long acronym for a very short word. And so we recently added a quantum downlink source that's going to be at 850. And so at the University of Calgary, so I'm actually located in Calgary. I work remotely for Thomas from there. So it's really great to be able to now visit my group after this conference. And so in Calgary, there's actually a receiver at their quantum ground station for 850 that they're currently using to link with Meteus, the Chinese satellite that's currently in orbit. And so they can use a similar receiver at that 850 for this new quantum downlink source when it's launched. And as I mentioned, because there's an uplink, so you can have multiple quantum sources on the ground. And so we can test also linking ground to space links. So fiber networks, atomic memories, trying different sources like a quantum dot source. And our goal is to demonstrate space QKD in Canada as well as globally because of our national ground stations as well as there's international partners. And then this isn't just QKD. You can also, we want to study what overall quantum links are. We can look at things like entanglement in relativistic settings because you've got now the space, like we've got like the macro along with the micro. And then the launch is scheduled for early in 2024. And so I'm not going to go through all this. I just wanted to have it up as a reference, and I can share these slides with the organizers if they want to distribute them. But this is the mission goals, requirements and goals for QEYSSat, and just some quick pictures. So when we were first demonstrating these prototypes and whether this could work in the lab, whether this is a viable receiver, can we do this free space QKD to a moving receiver? So this was one of the first experiments that Thomas's group did. And so they put the receiver in the back of a pickup truck, and then we have our transmitter that's also the current ground station location at IQC on campus, and then a kilometer away they drove the truck along the road. And got a viable key. And then that led to the designing of the QEYSSat payload. So we've got some of the specs here. And I just want to point out the fact that they're just, these pictures here are them mounting the payload, the test receiver into the airplane. Because after the truck demonstration, we went to the airplane demonstration where they flew with the door off. So you have to get the light in and out, right? So you have the receivers sticking out there, and you can see some images of the people out in the fields working in the transmitter trucks, right? And then you can also see some of our other team. And this is like a diagram showing one of the things that we test in the lab. So the free space link between the transmitter and receiver and all. Remember when I said it's not just physics, it's also engineering. So we've got like time taggers and detectors and analyzers and lots of optics. And then this is also a picture from one of our labs where we've got one of the telescopes, and then you've got this other receiver, and it's on this rail system so that it moves through the lab. And my colleagues, they were able to generate a secure key. And this is the plan for both up and downlink. And so for the mission, we're right now here in Q4 of 2022, and the launch is scheduled for early 2024. First, we demonstrate, they have the demonstration phase for the mission. So this is what all those mission goals and objectives and all that was. And then the science team will begin. And so what is the science team? What are all the people I'm coordinating? So we have the executive team, which is all of the government and NRC Ottawa and NRC Hertzberg, as well as the core team at IQC. And we're going to have a secondary ground station, and CSA is the primary. And then we have the Canadian team. So we've got researchers all across Canada contributing and some of them were giving talks today. So Fred, Stephanie, they're all part of the science team as well. And then we've got the international team, and this is still growing as I sign more members on. So we've got people in Poland and the UK. The UK teams are part of that RefQ project I was mentioning, so that's a great component to the project. And then we have DLR. DLR is in Germany. They're the German Space Center. So they're going to help with us tracking. Yeah. And I can't go through all this. So cool telescope, weather station, there you go. So thank you so much. And we're always looking for students, undergrad, graduate, postdocs. We're always looking for more people to join our teams because here's our prof, Thomas. And there's a QR code for our group website as well as the QEYSSat website that talks all about the mission as well as the science teams. And thank you to all of our sponsors. Thank you. Sorry.
Yeah, no worries. Thank you very much, Dr. Kuntz, for the talk.
Yeah.
We have time for a few short questions.
And I'll be available after if we want to talk more. Yeah.
Thank you so much for the presentation. In one of the slides, you had the positions of different satellites which are involved in QKD. What strategic benefits do you get from placing satellites at like different heights? Like what are they? Is a specific height especially beneficial, or like the closer you are to the surface, is that better?
Yeah, excellent question. You get advantages based on what your geographical locations are. So for example, if your country is located fairly far north, then there's going to be polar orbits or geo orbits that are going to work better, especially if your country is very, very large like Canada. So a LEO orbit, because you're about 500 kilometers above the ground, so the distance that you can see down, it's not going to be coast to coast, right? In order to get that distance, we have to go MEO or GEO. So you would think that, okay, then bigger is always better, right? But then the problem is you're further away. And so even though in this picture, you can see what they've done is if it's an uplink, then like see for the QEYSSat mission, how the beam is skinny at the bottom and then gets wider up at the top because of beam diffraction, right? So even if we send a perfect Gaussian beam, as pretty and beautiful as Wilson and his team can make it, right, out of those beautiful telescopes, it's still we have beam spreading. So when it leaves the ground at 10 centimeters, it arrives at the satellite like a few meters. So if you have a GEO satellite way up here, for example, this QEYSSat, they couldn't do an uplink. So, because you've got the first 20 kilometers is the atmosphere distorting your beam and causing loss. But then after that, it's just free space. Like, it's just vacuum, basically. So downlinks are actually better, you get more sustainable rates. So there are trade-offs of what orbit you use. It depends if it's an uplink or a downlink, because those things are affected by that. And yeah.
Hey, so you said the satellite's passband was somewhere in that 700 or 800 nanometer range?
780 to 795.
Okay, and I'm wondering what motivates that and if you have control and you can change that.
Totally. So, there we go. Let me show you a picture.
And I guess as a follow-up, I'm wondering if you can control it enough that you can take advantage of, I guess, the optical properties of the atmosphere to refract, and maybe even use something like the over-the-horizon radar technology to eliminate the satellite altogether and just bounce signals off the ionosphere. Yeah.
So I have a picture of, I don't know where it went though. Anyway, I'll have to send it to you later. But we actually have a study in 2015 where we were looking at what would be the optimal wavelengths to send through the atmosphere for an uplink, because you get atmospheric absorption, and so there's certain wavelengths you definitely don't want to use because it's like it's a vibration absorption line for oxygen or something that's in our atmosphere. And so there was 780, 850, and 1550. Those are all very good wavelengths for transmission for both up and downlink. But bouncing it off the atmosphere, so that would be tricky because of the scattering effects and all that, right?
Yeah, and you need a really long wavelength.
So like, are you thinking like way far in the infrared or like further, like radio wave?
Yeah, like megahertz range.
Okay, so there are people who look into quantum systems that work in the RF range, in the megahertz range, right? But trying to get them to do transmitters, like to do a transmission, like that's hard. So that's why we have to work in these visual ranges for, yeah. So I'm not sure if but it's possible. That's part of the exploration is what wavelengths work optimal for all these different quantum conditions, right? So we know light is really good for transmission. We know atoms are really good for memory, so we got that. But then what color does everybody want to work at? So like talking to the satellite might be one color, maybe talking inter-satellite might be a different color. Ground network is definitely going to be 15-50 because we just know silicon is good for that, right? For fiber. Yeah.
Okay, cool. Thank you very much.
You're welcome. Maybe do one more and then stop? Yeah. Sorry, I talk too much. Okay.
So this is a question back to the Alice and Bob instance of how, like, sort of the rectilinear and the diagonal bases that
That one?
they use to communicate. Yeah, exactly. My
Cool.
question is the polarizations, like to sort of like ensure or add an extra layer of security in how it's transmitted. The polarization states don't necessarily to be covered by these particular bases, just any bases where the entries are orthogonal, such that like it introduces an extra layer of decryption that one would have to do if they want to eavesdrop on it.
Yeah, non-orthogonal, the HV and DA have to be
No.
non-orthogonal.
Yeah,
Yeah.
I mean like the entries for the specific bases, HV and DA.
Yeah. Those just have to be orthogonal. That's right.
So it can't be anything.
Sorry?
So it could be any set of like any combination
Yes.
of entries, such that the two entries of each set are orthogonal and comparatively they're non-orthogonal.
Yes. Yes, they could be like slightly rotated, like 'cause whatever H is arbitrary, right?
Yeah.
So that's actually one of the beauties of this reference frame independent QKD that is a protocol we're also going to explore with QEYSSat, because like the satellite's reference frame is completely different from the ground's reference frame. So with this polarization stuff, it's like what's H on the satellite? So we actually, like the satellite's going to tell us what it thinks H is, and then we're going to align our ground station to that reference frame. But you can do it the other way too. You can define your your reference frame on the ground, and then transmit something to the satellite that tells it rotate this way or roll this way, or yeah.
And what would cause the reference frame of the satellite to deviate considerably, or like not even so?
Well,
considerably?
like the satellite's slowly rolling, I guess, as it's rotating. Like there's a very slow roll to it, so that would be slightly moving the polarization. I think it's like 1 degree for a pass. It might rotate 1 degree. So it's not a big rotation, but when you're dealing with trying to hit single photon detectors, like that's a big rotation.
That's super precise.
Yeah.
Okay, thank you.
Yeah. Thank you.
Right, thank you very much for the informative talk.
Thank you very much.
It's very fun.